Girish, can you check if 2-3 people are able to see the screen and hear me?
Hello, Dharmendra.
Yes, it's visible.
Okay. Can you see this slide name, title Lecture 14, Hypothesis Testing?
Yes.
Thank you. Apurva?
Yes, sir, I can see it.
Okay, thanks. Prince?
Yeah, it's visible.
Okay,
Okay.
thank you.
So we can start now. So as you know, we are discussing hypothesis testing, and surprisingly, the emphasis should be given to how the hypothesis is formed. Okay, what should be the hypothesis, the null hypothesis and the alternative hypothesis, rather than on the technique. Okay, so when you think of hypothesis testing, we think of Z critical and chi-square critical, chi-square observed, and so on. Those are matters of technique. The emphasis should really be on how is the hypothesis constructed. Okay, when you look at the problem situation, the data that is observed, based on the data and the problem situation, what is the null hypothesis? What is H0? So that emphasis is important, and our focus shifts from technique to this intuitive question of what is the correct hypothesis, null hypothesis for this problem, this data. Okay, so do please remember this point. And we are of course not doing traditional lecturing. All these are not for some examination, quiz, etc. We want to build a solid understanding on machine learning and data science. Request everybody to mute your mics, please. So that is the point. So to give an example, now suppose the administrative authorities of a city conduct a COVID test. Okay. Then, interestingly, this is a very interesting point. There are 3 entities involved in the situation with respect to hypothesis testing. Who formulates the hypothesis? What is the problem constraint? What is the data in front of me? 3 things. To illustrate this point, so in a city, COVID testing has been done by the municipality corporation. Now, if the test result comes out to be positive, then what is the belief? Suppose there is no symptom and the test result comes out to be positive. Then the person who has been tested and many of his friends, associates would think that the test is actually false negative, false positive. So even though the test says positive, the individual doesn't have it. Many times that is the hypothesis. This is the hypothesis formulated by people close to the person and the person himself also. Now, if this is told to a doctor, doctor surprisingly proceeds with the hypothesis, yes, the person is indeed positive. Okay. And also it depends on the time when this observation was made. At this time when corona is surging, people would be inclined to form the hypothesis that the person is corona positive. Doctors will almost always say so, but when they form the hypothesis, you will see in all medical reports, it is written as a disclaimer below that the conclusion should be compared with evidences from other tests. So you can possibly see that, like the definition of sentiment analysis, hypothesis testing also is pointing to an n-tuple. What is the hypothesis? Who forms the hypothesis? What is the observation? And at what time is the hypothesis formed? The same person, maybe after a year, would form a completely different hypothesis. So hypothesis testing points to the formation of an n-tuple, just like sentiment analysis. In sentiment analysis, the opinion holder, the time at which the opinion was held, the opinion per se, the entity, and the particular feature of the entity. For example, color of a camera. So here, hypothesis testing is at least a 4-tuple problem: the hypothesis holder, the time of the hypothesis, and the data. So I should have added a slide with this 4-tuple definition. This is what I thought should be a good framework. So I'll add that slide. So let me proceed going slowly and from very simple discussions. So here is something I have done. I have made 10 tosses of a coin. So the situation, I suppose, is clear to you. There are 10 head and tail values in front of me. Okay. So since the data is in front of me, observation is in front of me, the likelihood of the data in terms of the parameter can be computed. So these are different situations. One head has appeared. Then by maximum likelihood estimate, the probability of head, which is the parameter theta, is 0.1. Then the probability of the observation, which is 1 head and 9 tails, will be 0.1 to the power 1 into 1 minus 0.1 to the power 10 minus 1. Okay, so this is the likelihood of the data. Okay, do not get confused by asking where is the n choose k component of the formula. N choose k is needed when we give the probability of the number of heads. But here we are asking what is the probability of the observation in front of me, probability of the string of heads and tails. So for 1, the probability of the observation, the data, is 0.0387. For 2, it is 0.0067, 3.0022, 4.0011, 5.0010, and then symmetrically it rises again. 6.0011, 0.0022, 0.0067, 0.0387. So this is the picture. The probability of the observation goes on decreasing until the probability of head is 0.5 and then rises again. Okay. So just as a digression, is this an expected behavior? The situation is we observe the number of heads and apply the principle of maximum likelihood and say that the probability of the heads, which is the parameter controlling the distribution, is k by n. And as k changes from 1 to 9, I purposefully avoid the situation of 0 head or 0 tail, because 0 to the power 0 is undefined. So the values are varying from 1 to 9. Then you see the probability of the observation first falls and then rises. Now a digression, a curiosity. Is this an expected behavior? Okay, nothing to do with hypothesis testing now. Why should the probability fall and then rise again? So a bit of mathematics helps here. So likelihood of the data is theta to the power k into 1 minus theta to the power n minus k. Since we are using maximum likelihood principle, we obtain theta from k by n. So k and theta are mutually dependent now. Both are variables. So I express everything in terms of one of the controlling variables, that is theta. So then L can be written as theta to the power n theta, because k equal to n theta, into 1 minus theta to the power n minus n theta. If I take the log of this likelihood, then LL is n theta log theta plus n into 1 minus theta log 1 minus theta. I differentiate log likelihood with respect to theta, and I get n into 1 plus log theta plus minus 1 minus log 1 minus theta. Just a differentiation of this expression with respect to theta. Now equate this first derivative to 0. Then I get log theta equal to log 1 minus theta. Theta gives me 0.5. So as k varies, the extremum is reached at k equal to 5, or correspondingly theta equal to 0.5. So extremum is at theta equal to 0.5. But is this minimum? So again, appeal to calculus. So d square LL d theta square, take the second derivative. The first derivative is n into this quantity. Second derivative comes out to be n into 1 by theta plus 1 by 1 minus theta. Now theta is 0.5. So this quantity is positive. So the second derivative is positive. So at theta equal to 0.5, we reach extremum. And not only is this extremum, this is also the minimum point. So the probability of the observation as k varies from 1 to 9 goes on decreasing, reaches minimum at k equal to 5 and increases again. Mathematically also this is established. But I leave it to you to think, why is the probability decreasing and then increasing again? Why does the probability of the observation reach a minimum when k is equal to 5? Okay, come up with an intuitive explanation of why this should be the case. Mathematically, it is established. Now, for this situation, I form a null hypothesis. So now I come back to null hypothesis and discuss the design of the null hypothesis, the construction of the null hypothesis. What is the guiding principle in formulating the null hypothesis? The guiding principle is the following. I will say it twice. The null hypothesis is formed such with the intent of negating the hypothesis with the help of the data. Okay, that is the purpose. There is one more principle involved under the null hypothesis. So the key phrase here is under the null hypothesis. If the null hypothesis is true, then by maximum likelihood estimate, what can we say about the data? So we would like to follow a framework that if the null hypothesis is true, the data is unlikely. Okay, according to maximum likelihood framework. But data cannot be unlikely. Data is in front of me. So the null hypothesis must be rejected. Okay, so this is the crux of the matter for hypothesis testing. Should have added a slide with these two critical points. We'll add them. I'll just repeat these 2 points. One, the data null hypothesis is formulated such that the data should challenge the hypothesis and reject it. Second, formulate the null hypothesis, and under that umbrella, through the maximum likelihood framework, try to prove that the data is unlikely, the observation is unlikely. But then ask, how can that be? Data has happened. This is the reality in front of me. So the hypothesis must be false. So this is the crux of the matter for hypothesis testing. Okay, critical, observed, H0, HA are just matters of notation. Once you take this point of view for hypothesis testing, everything else falls in place. Now to illustrate this point, let me say that the coin is unbiased. Okay, and then examine various data situations. So if the coin is unbiased, then theta must be 0.5 and H0, the null hypothesis, is theta equal to 0.5. I proceed with this hypothesis, okay? And then I know that the data likelihood is theta to the power k into 1 minus theta to the power n minus k. So assuming theta equal to 0.5 and assuming different values of k, I can get the data likelihood. So let me illustrate this, okay? And this discussion is mainly to show you what does it mean to say under this hypothesis, the data has this property. Under a hypothesis, the data has the property. What does this expression mean? So to illustrate that, I show you a set of steps. So now I am proceeding with the assumption that coin is unbiased, theta equal to 0.5. What happens to the data? Suppose the data is that h is equal to 1 out of n equal to 10. That means only one head has appeared and there are 9 tails. So this is the observation in front of me. So by maximum likelihood estimate, which is underlying principle, the data must return theta equal to 0.1. Okay. So our discussion could have stopped here. We would have said that, well, theta observed is 0.1, theta critical is 0.5, compare them and reject the hypothesis. So since theta is not equal to 0.5, isn't it automatically rejected? What more is needed? No, I would like to show that you also can compute the probability of the observation. And since the situation is not always as simple as coin throw, you have to work with the observation. Okay, you have worked with the observation to get theta equal to 0.1. Data and maximum likelihood principle gave you theta equal to 0.1. Let us look at it from another point of view. The probability of the observation is 0.0387 if the likelihood principle is correct and if the data in front of me is correct. So then the probability of the observation would be 0.0387. However, under H0, null hypothesis, the probability of the observation is 0.0010. We note that there is a difference between the probability of the observation under null hypothesis and under maximum likelihood principle. Whom should I trust more? Okay, maximum likelihood principle or the null hypothesis? Maximum likelihood principle is well established, hundreds of years of history. Null hypothesis has been formulated by me just now. So this is vulnerable. Now the data in front of me is that there are 4 heads out of 10 tosses. Maximum likelihood and data says theta equal to 0.4. Then the probability of the observation under maximum likelihood is 0.0012. And under null hypothesis, theta equal to 0.5, probability of the observation is 0.0010. Now you see the distance between the probability of the observation and the probability under maximum likelihood has decreased. So if I say this is observed 0.0012 and this is critical 0.0010, which arises because of null hypothesis, then the distance has decreased. So I will not be able to reject the hypothesis that the theta is 0.5. Let's proceed. H is equal to 5. There is no distance between likelihood based probability of observation and null hypothesis controlled probability of observation. H equal to 7, data in front of me, 7 heads, 3 tails. Now the probability of the observation is 0.0022 by maximum likelihood principle. And the probability of the observation under null hypothesis is 0.0010. This continues. Now the distance has increased. So what am I driving at? This is an illustrative example. Okay, there is a notion of distance between two quantities. These two quantities are, one of these quantities is very important. That quantity is the result of assuming the null hypothesis. The null hypothesis gives one quantity and another quantity comes from the observation. The distance between them dictates whether the hypothesis should be rejected or accepted. So I hope this principle is clear to you based on this example. Data returns something observed. Null hypothesis returns something critical. Compare them and then reject or accept. The absolutely solid framework for hypothesis testing, probabilistic hypothesis testing. We have other instruments at our disposal. Cross entropy study can be done. Now, if I assume the null hypothesis, theta equal to 0.5, then the probability distribution for head and tail is 0.5, 0.5. These two quantities should add up. Now, I can invoke cross entropy distance between the probability distribution under null hypothesis and the probability distribution according to data. So the cross entropy is minus t log O minus 1 minus t log 1 minus O, where t is target, O is observed. Now observation is based on the number of heads, 1, 2, 3 up to 9. And I see that for 1, the cross entropy between 0.1 and 0.9 and 0.5 and 0.5 is 1.2. For k equal to 2, the cross entropy between 0.5, 0.5 and 0.2, 0.8 is 0.92. Then 0.78, 0.71. At 5, it becomes least, 0.69. Then the cross entropy increases again. So I could have taken this path also. I have worked with probability of the observation. Now I resort to cross entropy distance. And that also gives me a way of measuring the distance between observed and critical. Do remember this point. The critical quantity comes under the null hypothesis. Observed quantity comes by virtue of the property of the data. And we study the mismatch between them. Now I can take the difference between the probability of the observed data and probability of the observed data under null hypothesis. That would be a measure of the distance. Cross entropy also gives me a distance between critical and observed. But what is done in the field is to appeal to properties of normal distribution. So we'll come to that. Again, we do a bit of digression and we go to logic, which again has a very well established method of hypothesis testing, of course under a different name. And those of you who attended my lecture on explainability and cognition would remember this particular example, but I would like to repeat this. What is the design in mind about invoking logic? Why are we looking at logic? Because logic has its own method, deterministic method, of establishing consistency of hypothesis. Consistency of a goal, sometimes it is called goal, sometimes it is called hypothesis, sometimes it's called inferred statement, and so on. It has its own method, non-probabilistic. But to complete our picture of hypothesis testing, we need to look at that body of knowledge also, which is based on deterministic principles. So let's look at their method, the method, well-established method of logic, about 2000 years old, both from Greek tradition, Aristotle, Plato, and so on, and Indian tradition of Nyaya Shastra, which is logic. Only thing, probability was not there, interesting. And historically, it is interesting to examine why those ancient thinkers did not consider probability, or did they? Okay, so that's an interesting question in the mind of scientists and researchers. So keep that question in mind and think why probability did not play much role there. Probability became very prominent with the work of Fisher in England. When was this? About 18 something, I believe. I may be wrong. But why probability did not play a role is interesting. Now, this example is the Himalayan club example. Can somebody verify that you are seeing this example, Himalayan club example?
Yes, sir.
Yeah, okay. So this is given in the form of puzzles in competitive examinations. We are told that A, B, and C belong to the Himalayan club, and every member in the club is either a mountain climber or a skier or both. A likes whatever B dislikes and dislikes whatever B likes. A likes rain and snow. No mountain climber likes rain. Every skier likes snow. And we ask, is there a member who is a mountain climber and not a skier? Okay, based on the facts and rules given. Now, since we have left probability behind for a few minutes, we look at the language of logic. Logic brings in facts and rules. Facts are cold pieces of information. The fact that A is a member of the club, B is a member of the club, C is a member of the club, these are facts. But every skier likes snow is a rule. You'll have to invoke universal quantifier and say for all x, skier x implies likes x snow. Can you also spot other rules? So this is the interesting part about language processing. Rules need not always appear in the form of if-then construct. No mountain climber likes rain. There is no if-then here, but there is a rule. If X is a mountain climber, then X does not like rain. Every member in the club is either a mountain climber or a skier or both. So for all x, member x implies mountain climber x or skier x. So this is also a rule. So in classical AI, we distinguish between facts and rules. Okay. So just to be a little more technical, facts are called zero order entities. Rules are called first order entities. Okay. They involve variables. Facts involve constants. So this is captured by means of predicate calculus. Many of you are possibly doing the AI course. So A is a member is written as member A, member B, member C. For all x, member x implies mountain climber x or skier x. If x is a mountain climber, x doesn't like rain. If x is a skier, x likes snow. If B likes x, A doesn't like it. If B doesn't like x, A likes it. A likes rain, A likes snow. And the question is there a member who is a mountain climber and not a skier? So now it is interesting that you can find the answer very quickly by looking at the problem statement. If we use machine learning and data science terminology, then we'll say based on the data given, you can answer this question very easily. So the chain of reasoning is small and simple. A likes rain and snow. So B cannot like rain, B cannot like snow. Since every skier likes snow, B cannot be a skier. Law of contraposition. Now, B is a member of the club. B is not a skier, and every member is either a mountain climber or a skier or both. So B must be mountain climber. So the answer to this question, is there a member who is mountain climber and not skier? The answer to that question is yes. And as a side effect, we obtain the answer as B. B is that member. Now, what is the method of logic to answer this question? This, by the way, also is called intelligent question answering. The method of logic is to follow the path of contradiction. Okay, follow or take an aggressive stand. Okay, antagonistic stand. I don't believe that there is a member who is a mountain climber and not a skier. So a goal is set. A goal is set, which is this: not for all x, not member x, or not mountain climber x, or not skier x. So this comes from negating the existential expression. There exists x, member x, and mountain climber x, and not skier x. If you negate this, then existential quantifier becomes universal by law of predicate calculus. When negation moves inside, you apply De Morgan's law repeatedly, negate the literals, and turn AND operation to OR. And this is the expression you get. This is becoming a conjunctive normal form expression, which is added to the knowledge base. Okay. And after adding it to the knowledge base, we try to prove that the data has become contradictory now. The knowledge base has become inconsistent. So for that, there is a very well established algorithm called resolution refutation. And we establish a resolution refutation tree. So it goes like this. You take two clauses and resolve them. The rule is that the literals which are positive and negative get dropped, and the variables get bound to constants. So this rule that whatever A likes, B dislikes, and A likes snow, establishes the new knowledge that B does not like snow. Okay, so this is called the process of resolution. And refutation comes when at the end you show a null clause. I think it is not coming on the screen. This is an inverted tree. No, this is a tree. and the root of the tree is an empty box called the null clause. So the resolution refutation algorithm proceeds with the explicit aim of arriving at a null clause which indicates contradiction in the data. And why did the contradiction arise? There was nothing contradictory about the data. A is a member, no skier likes no, etc., etc. All these facts and rules which are given, none of them are contradictory. None of them are false. So what would be false? The false thing would be my goal, that there is nobody in the club who is a mountain climber and not a skier, because there is indeed a person. B is that person. So here I have arrived at a contradiction by adding something to the database or the knowledge base. And since the data cannot be wrong, hypothesis must be wrong. So the hypothesis was that there is no mountain climber, there is no member who is a mountain climber and not a skier. That is false. Okay. So see the methodology of logic. There is one fundamental similarity between both methods. Assume a hypothesis. Let us call it null hypothesis, because this hypothesis we are proceeding to demolish. Assume a hypothesis and then show a contradiction with respect to the data. And that since data cannot be wrong, the hypothesis will be wrong. So in probabilistic hypothesis testing also, we try to establish a contradiction, just like in logic. But what is the crucial difference between probabilistic hypothesis testing and resolution refutation in logic? What is the crucial difference? The crucial difference you should note carefully is determinism versus non-determinism. Determinism versus probabilistic. Here, every clause that is generated through resolution, it has to be true. There is nothing gray. Okay, it is either true or false. False is indicated by the null clause. So the method is completely deterministic. In probabilistic methods, we have to the probability of something being false or true, not deterministic statement. This is indeed true. This is indeed false. No, with so much probability, this is true or false. Okay, so this is the probabilistic method, and the contradiction is also within bounds of probability. So let's proceed forward. And here I have recorded that the null hypothesis is that the club does not have any member that is a mountain climber and not a skier. So key question is, under age 0, is the observation valid? Or is, in terms of machine learning data science, is the hypothesis consistent with the data? And by resolution refutation, we establish that the hypothesis is not consistent with the data. So reject the hypothesis. Now, the important fact here is data cannot be rejected, and data is indeed the gold. Now let's take a data science point of view to this Himalayan club example. The data are the following pieces of information. A, B, and C belong to Himalayan club. Every member in the club is either a mountain climber or skier or both. A likes whatever B dislikes and dislikes whatever B likes. A likes rain, A likes snow. Now, no mountain climber likes rain. Every skier likes snow. So all these are data items and they cannot be trifled with. And the null hypothesis, there is not a single member who is a mountain climber and not a skier. And age 0 is inconsistent with the data. We apply logical inferencing, which is resolution refutation, deterministic. Okay, nothing probabilistic about it. Now, let us try to remember what we did for chi-square testing. Now, my aim here is to go to probabilistic distance measurement. Okay, we in the beginning of the lecture, we computed probability of observation and probability of observation under null hypothesis, and we could take the difference and have a kind of distance computed, or apply cross entropy based distance. All that is fine, but we have looked at a method of distance computation and giving a kind of confidence to this distance through probability. That is when we applied chi-square test. So let's recall one of the problems we took, tossing a die 120 times. So a die was tossed 120 times, and the face 1 appeared 25 times, 2 appeared 17 times, 3 15 times, 4 23, 5 24, 6 16. Now, can I say that the dice is fair? So I will form the null hypothesis that the dice is fair, okay, and then see if the data becomes contradictory or not. Same methodology. So if I assume that the dice is fair, we'll get for each face the number 20. There are 120 throws of the dice. So each face should appear 20 times. And the fact that it doesn't appear 20 times does not allow us to conclude immediately that the dice is not fair, because the framework is probabilistic. There are many controlling parameters: wind speed, pressure of my hand, my sitting position. There is an imponderable number of parameters which can control which face will appear when we throw the dice. So our framework necessarily has to be probabilistic. We have no option other than saying that this decision has to be under uncertainty. And probability is the instrument to use here, no other instrument. So expected are all these 20s, and observed frequencies are 25, 17, 16, and so on. I can neither deterministically accept the hypothesis that the dice is fair, nor deterministically reject the hypothesis that dice is fair. I cannot do anything deterministic. I have to use probability because there are too many controlling parameters and unknown. So here you would recall the methodology. First, we look at the frequency of the observations. 1 appears 25 times, 2 17 times, and so on. Expected values are 20 for each phase. I calculate observed minus expected, get 5 minus 3 minus 5, and so on. Get O minus E square and divide it by expected. So I get 1.25, 0.45, 1.25, and so on. I add all these O minus E square by E and get a value of 5. So this quantity 5 is called chi-square observed. Okay, chi-square observed. And then we are required by the methodology to find out chi-square. Now there are 6 classes. So the degree of freedom is 6 minus 1, 5. And significance level also I have to fix before beginning the game. Okay, so I cannot change the rule when the game has started. So before observing the data and processing the data and making various comparisons, I have to a priori declare my significance level alpha is 0.5. Now, chi-square table gives me, under these conditions, that degree of freedom is 5, significance level is 0.5. What is chi-square critical? Well, chi-square critical comes out to be 11. Maybe some of these things you have forgotten, needs brushing up. The lectures are all there. But the data is returning me chi-square critical to be 11 under the null hypothesis. Okay, if the if the dice was fair, then the expected values are controlled by that hypothesis. It is all 20. Okay, if the hypothesis was different, these expected values would be different. So under null hypothesis assumption, I get chi-square equal to 11. And then the methodology is that chi-square observed, if it is less than chi-square critical, then we cannot reject the null hypothesis. And therefore, the dice must be accepted to be fair based on the data and based on the technique that we have adopted. Here I draw your attention to something we have learned in terms of probabilistic framework. In logic, Himalayan club example, we rejected the hypothesis by resolution refutation deterministically. Each intermediate step was deterministic, completely true. At the end, a null box, which indicates falsity or contradiction in the data. The data became contradictory, okay, by adding the hypothesis. So completely deterministic methodology. When we looked at the coin, 0.5, 0.5, and then the data of number of heads, 1, 2, 3, up to 9, we applied probability. No doubt about this. We applied probability. And we also observed distance between probability of observation and probability of observation under null hypothesis. Probability. But the distance and the accept reject threshold was unprincipled. Cross entropy value is so much. Shall I reject or accept? Based on what principle? That principle was not clear. So chi-square is giving me a methodology for making that threshold principled. We'll also see as we go forward that the central limit theorem and interval estimate again gives me a principled method of computing distance and accepting or rejecting the hypothesis based on a threshold. So what is the crux of the matter now? We want a threshold which will give me reject or accept possibility. And that is done through comparison of observed with critical. The underlying distance is a probabilistic distance based on the area under normal curve, where we have to make use of intervals under normal curve. Okay, some positive value to plus infinity or from some critical quantity to plus or minus infinity. One tail test, two tail test. Okay, all these are nothing but a principal method of computing the distance between two quantities, one under null hypothesis, another based on the property of the data. Okay, so that is it. And in chi-square also we operate with null hypothesis. So the key points now are more investigation into null hypothesis construction. What happens if the null hypothesis is accepted, and then computing probabilistic distance and then rejecting, accepting based on that. That is all there in hypothesis testing. But key point once again is this construction of null hypothesis. That is really an art. You have to understand the problem very carefully, and you have to understand the property of the data. So my favorite analogy here is when we write a computer program, the most difficult step is to decide the names of the variables. Variable declaration. We have to give the variables proper names so that they indicate their function. This is a very difficult and critical step. And the next critical question is, how many variables do we actually need? Those things are matters of experience, art, and skill. In hypothesis testing also, declaring the null hypothesis is a matter of art, experience, and skill. Because once the null hypothesis is established, so many things follow from that hypothesis. But there is cold data in front of us, Data tells something, hypothesis, null hypothesis tells something else. If they are not consistent with each other, reject the null hypothesis because you cannot reject the data. Okay, that is all. We'll continue this discussion with both intuition and solid techniques as we move forward. Okay, are there questions, comments?
Hello, sir.
Yeah.
Sir, how would one decide that this experiment needs a probability-based hypothesis testing or logic-based?
Very good question. So how do I know I should remain in deterministic framework or have to adopt probability? How do I know this? This problem is amenable to probabilistic solution or to deterministic logic-based solution? How do I know? Very good question. And I don't think I can give a very satisfactory answer. So I would say that first and foremost, if the data in front of us depends on many parameters which are not known, there are many controlling parameters and not all of them are known. And these parameters also vary from situation to situation. A, B, and C are members of Himalayan Club. This doesn't vary from situation to situation. There is nothing uncertain about it. All skiers like snow. There is no uncertainty about it as far as the problem statement given in the book is concerned. But we know that this is not a black and white statement. Not all skiers like snow. And when they like snow, they like it in various degrees. So when there are these kind of parameters, many of which are unknown and many of whose values are random is the keyword, then we have to use probabilistic methods. Coming to a practical situation, when we conduct NLP experiments, when we build part-of-speech tagger, for example, and claim that the accuracy of the part-of-speech tagger is 95%. Some company says that 95% is the accuracy of the part-of-speech tagger. Do I adopt a deterministic method or probabilistic method? Now, when I take samples of data and do part-of-speech tagging, I observe different accuracy values. It is not always 95. Okay, so in this situation, since batch to batch, sample to sample, the value will vary, I'll have to use probabilistic method of hypothesis testing. So I know this doesn't answer your question completely, but the sum and substance is if there is randomness in the situation, you have no choice other than use probability.
Okay, sir. Okay, understood. Thank you so much.
Who was asking this question? I'm sorry.
Sir, Ritvik from Anvishan Setu.
Oh, okay. Any other question, comment, point? Any question comes to your mind? Comment. Okay, so if there is no other question, we'll stop the lecture now and meet again after 2 weeks. By the time I hope you would have churned this point about hypothesis testing your mind quite a lot, especially null hypothesis. Okay, go after the null hypothesis. That is the crux of the matter. Okay, and then we'll have our work update meeting for the information extraction group 2 from 11 o'clock in a different link. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.